Molecules play a very important role in the process of first star formation in the early universe. After the Big Bang, the hot ionized matter could not form the stars directly. It must have cooled down first to form atoms and molecules and gas clouds. After further cooling, these gas clouds could collapse gravitationally and form the first stars. In this process, the molecules are very important coolant. So to understand how and when the first stars were born, we need to know the amounts of the molecules in this early phase. Since it was only hydrogen and helium elements which were available in the early universe gas, one could combine those elements only in a handful of molecules. Out of these combinations, it is the Helium H+, an asymmetric molecular ion, which is the most efficient molecular coolant. If it was abundant enough, one could actually expect that it cools the clouds on macroscopic scales. Unfortunately, at the moment, the abundance of Helium H+ in this era is not known precisely enough to tell.
Yeah, one needs to know not only how the Helium H+ molecules are formed, but also how they are destroyed. Since they are electrically charged, they are very vulnerable and can easily be destroyed by colliding with the electrons that are around in the cosmic gas. In this case, the molecule will disintegrate very fast, and you get a helium and an H, which rapidly disappear and never find each other again. For this reason, you really have to know the rate of the destruction process under the condition of the cosmological environment. To obtain this rate, in principle, one could perform molecular quantum calculations, which, however, are still very uncertain. And for this reason, we have to perform laboratory experiments, really mimicking the conditions that we have in space.
So how to create space-like conditions in the lab? First of all, we have to reproduce the low temperature relevant for the space. Those lies at some 100 Kelvin. This is about 200 centigrades below the room temperature. Next, we have to be able to store the ions at these conditions for tens of seconds or even for minutes. And last, we have to make sure that the ions collide only with the electrons and not with other molecules, for example, from terrestrial atmosphere. We have built such an environment in a form of a storage ring called CSR in Heidelberg Max Planck Institute for Nuclear Physics. Simply speaking, we created a closed-loop chamber of about 35 meters in circumference and pumped the atmospheric molecules away to reach vacuum. At the same time, we cool down the complete chamber so that the stored Helium H+ molecules feel the conditions as in the universe. Then we introduce some electrons and measure how fast they destroy the stored Helium H+. In reality, implementation of such a storage ring is technologically very challenging. In fact, from the first idea to build CSR, it took over 10 years of development before we could start the first experiments.
How do we measure the reaction rate? The Helium H+ reaction with electrons produces, as in space, a neutral hydrogen atom and a neutral helium atom. And these two atoms we observe on our detector. We really count them one by one. And then we also measure the number of electrons and ions that we mix in our storage ring interaction zone. With this, we finally have a quantity which is calibrated and which gives the reaction rate in such a form that it can be used in the cosmological models.
So what did we find? After the Helium H+ cooled down internally, we have observed that the destruction rate by collisions with electrons was surprisingly low. Actually, it was much lower than the previous results from experiments performed at room temperature. This means that under the cold conditions of clouds in the space, the Helium H+ has much higher chance to survive. In fact, we conclude that the abundance of Helium H+ will be at least 20 times higher than thought so far.
The new data help to improve the models for the first star and galaxy formation. This is actually an interplay of experiment and theory. both molecular quantum theory and the astrophysical model need the input of experiments in order to become as reliable as possible. In addition, one is building new large telescopes which will become more powerful in observing the objects of the early universe. And the goal is to obtain new information on this first star and galaxy formation. For example, the James Webb Space Telescope that will be launched very soon will probably produce a very large amount of spectroscopic data that contain the fingerprints of molecules. In order to understand what these data really mean for the composition of the universe and the processes there, it is more and more important that the building of large telescopes and the experimental research in laboratory astrophysics go hand in hand in order to expand our understanding of the universe.
We have shown that there could have been plenty of Helium H+ in the early universe. And now it's up to our astrophysical colleagues to tell whether Helium H+ was the important coolant to help the formation of the first stars.